So structure of atom is the uh, first theory about the structure of atom. The presence or existence of atom was given by Dalton atomic theory that we have seen. So just let me quickly go through the points of orally Dalton's atomic theory. Yeah, Maha, can you tell me any of the points? Nabila? Dalton's atomic theory actually we have studied law of conservation of mass, okay, law of chemical combination. So when the substances react, they react in fixed ratio, okay. Actually, that is the ratio of their number of atoms, okay. So basically, that all those uh, law of conservation of mass, law of chemical combination, led us to think that the matter is consist of atom. Okay, normally anything if you take this as a matter that we know. So if you so everybody wanted to know what it is made up of. Okay. So suppose if you keep on breaking it into smaller and smaller particles, so ultimately you will end up with the smallest particle, which is known as atom. Okay. So smallest atom is the smallest indivisible particle of the matter. Yeah. This is matter is made up of atoms. Okay. Now we know that atoms can be divided, but as per Dalton earlier was not aware of these further structure of atoms. So he just told that the matter is made up of atoms. Okay. It is the smallest particle of the matter. Smallest indivisible particle of the matter is known as atom. And atom, uh, suppose if you take gold or if you take silver, so all atoms of gold will be same, but they will be different from atom of silver. Got it? All atoms of silver are same with respect to mass and chemical properties. All atoms of gold are same, but atoms of one element are different from the atoms of the other element. Got it? So these were the points given by Dalton. At that time, the theory was not much developed, but today we know that these points are approximately true, not perfectly true. Indivisible, now we know that the atoms can be further divided into electron, proton, and neutron. So these are the drawbacks of Dalton atomic theory. Because Dalton gave its theory long back. That time he was not aware of the further smaller particles present in an atom. Now we know that uh, the atom is made up of electrons, protons, and neutrons. Atoms of an element have same mass and physical and chemical properties. So atoms of any one element are differ from the atoms of other element, but within an element all atoms are same. But now we know that within an element atoms can have different masses also, and those atoms are known as isotopes. That we will discuss further in this chapter. Okay. And what happens in a chemical reaction, Nabila? What happened in a chemical reaction? Chemical reaction, do new atoms are formed?
Compounds form or
Yeah.
break.
Yes. So new atoms are not formed in a chemical reaction. The atom recombine with new type of atoms. The atom remains same. Got it? Maha, is it clear? So atoms remain same. Number of atoms remain same, and that's why we, if you remember, we had law of conservation of mass because the number of atoms remain same. Okay, but they recombine in a new manner. They recombine in a new manner to form new compounds. Okay, so that we already know, and that's why we had the law of constant composition. Okay, constant composition means if you take carbon dioxide, it has carbon and oxygen always in a fixed mass ratio. Okay? And you had law of multiple proportion that we had discussed, right? So this is basically about the Dalton's atomic theory. Okay, but this is now we know atoms can be divided into further into smaller particles, subatomic particles. And what are those subatomic particles? Can you tell me?
Protons, electrons, neutrons.
Yeah. Subatomic particles. Okay, and now we know, but actual reality is today we know more than 26 subatomic particles. Okay, 26, more than 26 types of subatomic particle that you will study at higher level. Okay, but as of now we are aware of the three types of subatomic particles, and they are electrons, protons, and neutrons. Got it? And where these are present, where these particles are present,
Inside atoms.
In a
in an atom, where they are present actually within an atom. Electron.
Electrodes and
Hmm.
scattered around.
Yeah, there is a nucleus. Okay, but this was later discovered. Okay, I'm telling in a quick manner, right? Because we are going to discuss them in detail. So their protons and neutrons are present in the nucleus, and electrons are moving around the nucleus. Okay, so we are going to discuss the discovery of subatomic particle. We started with Dalton. That Dalton told that there are the particles are made up of atoms. Okay, and later we need to know what atoms are made up of. Okay, atoms. Now we know already because we have studied this in the first chapter, some basic concept of chemistry also, that atoms are made up of electrons, protons, and neutrons. Okay, but how they were discovered? So first is the discovery of electrons. Okay, So how they were discovered? Can any one of you tell me? Maha, Nabila, how the
So there was a discharge tube experiment.
yeah cathode ray they were discovered. Discovery of so first is the Michael Faraday did some experiment with the electricity. Okay, and later it was the cathode ray experiment, okay, or the discharge tube experiment. Or the discharge tube experiment is known as discharge tube. Okay, and that led to the and this experiment was carried out by William Crook. Got it?
Yes.
So what happened, Maha, Nabila? Then, can you give me some example of some objects in our daily life which we use, uh, where the cathode ray tube is being used?
Secondary.
Any example of cathode rays tube? It was carried out in a cathode ray tube. Okay, you have a tube, glass tube.
Electrolysis process, like the refining of sodium
Yeah,
or like
yeah, that is there. In our home, any equipment which has cathode ray tube. Okay, this experiment was performed in
That's
a glass tube known as cathode ray tube. CRT. So have you seen black and white TV long back we had, or the computer monitors? Okay, when we were in college that time we had very huge monitors. Now we have LCD and all, very thin. Okay. In earlier time we used to have, when we were kids, I remember, a very huge TV. Okay, it had a width on the back side. Okay, very huge. Okay, that TV, if you, or the computer screen monitor, if you open it up, you will have this kind of appearance and some electrical wires connected to this. So these are the cathode ray tubes that were used in electrical screens. Okay, in the earlier televisions and monitors, computer monitors. Okay, these are the CRT tube, cathode ray tube. Okay, so how this glass tube, simple looking glass tube, helped us to discover electrons? Okay, so because we can't see electron, they are very small, very small. How they uh, how it helped us to discover the electron? So first of all, this cathode ray tube, the air is sucked out of this cathode ray tube, right? And why it is sucked out? Because otherwise the electrons will not be able to move. This is air is sucked with the help of vacuum pump. Air is being removed. So it even if we remove the air, doesn't mean that it will not have any air. There will be some very little of very less few particles of air will be there. Okay. And these are the metal electrodes, and they were connected to battery. and very high voltage was applied. Okay, 10,000 volts. DC, direct current. Okay, very high voltage was applied. This is the positive and negative. I will make this as positive. And this smaller one is negative. So this is the negative electrode and this is the positive electrode. Positive electrode is known as anode and this is known as cathode. Okay. So there is a high positive and negative charge. High voltage is applied under a very low pressure. So what happens under so in our daily life also we may observe the effect of electron, but we are not able to see them. You take a scale, okay, plastic scale, and when you rub it with the synthetic cloth, okay, you might have, or when we wear the synthetic cloth, you might have seen that they get attracted to the skin, or when we rub a scale, plastic scale to a synthetic cloth, what we see when we bring it to the close to the bits of paper, the bits of paper get attracted. You might have done that experiment in your junior classes. Okay, all of us know that is because of the electrons, because of the rubbing, that some of the electrons may get transferred from that scale to cloth or cloth to scale. So there is an imbalance of electron and that's why there is a charge. Okay, before understanding this experiment we should know that if there are two same charges, positive and positive, they will repel and opposite charges will attract. Okay, that we know. It is just like the magnetic field. Two north pole will repel and north and south pole will attract. Okay, that is the magnet, that was the magnetic force. Here we are talking about the electrostatic force of attraction. So if you have same charges, two same charges, they will repel each other. Opposite charges will attract each other. Okay, so now how this experiment was done? Suppose a very few atoms were left because all the air was sucked out. So let's say very few atoms. Atom as a whole is neutral because the protons and electrons are equal. We know that. Okay,
So what are those circles?
and these are the atoms. Okay, right. I'm just drawing atom. So what happened is I will remove them. Okay, just to make you imagine that there are a few atoms left and they were neutral. But when the atoms were neutral and when you apply very high voltage of 10,000 volt, what happened? The charges of the atom, the positive charge particle of the atom will get attracted towards the negative. Okay, and negatively charged particle will get attracted towards the positive. Okay. So the atom is actually torn apart into positive and negatively charged particles. Do you agree with it?
Yeah.
So atom was neutral because all the positive and negative charges were together. Okay, so Dalton's were not had not thought of this. So he thought that atom is a single entity, but it is not a single entity. It is made up of small particles, positive and negatively charged. So high voltage was applied. Okay, and what was observed? This voltage will pull apart the positive and negative charges. Okay, but initially people were not aware of that much details, so they concentrated only on the negatively charged particles. But not only negative, positive charged particles were also generated, which were discovered later on. So what happens? Uh, they observed that at a very high voltage and a very low pressure, this tube will start glowing. it will start glowing, and that indicate that there is a flow of current through the tube. Flow. And why we took very low pressure, now it is clear. This current can flow only if you have a very less number of atoms, because if you have lot of air in it, this current will, particles will not be able to flow. They will be stopped by the number of air particles in between them. So we took very few particles, okay, and applied very high voltage. The atoms splitted, torn apart into positively and negatively charged particles. Initially, people were able to focus on the negatively charged particles, and these negatively charged particles were known as cathode rays. These negatively charged particles are none other than the stream of electrons. They have a negative charge. Is that clear? So how it was later verified that this is negatively charged, these are electrons. A lot of other experiment was, this is the basic idea of the cathode ray. What they did, they applied the phosphorescent material. This is phosphorescent material, zinc sulfide. Zinc sulfide, and what happened when these electrons were striking this is used to detect the charged particles. Okay. So whether you have a charged particles in your room or not, you can take some zinc sulfide, okay, put it, and wherever the charged particles are going to hit that zinc sulfide, there you will have find spots glowing. Okay. So what people observed, that they observed that when this cathode ray had zinc sulfide coating put on one end, that zinc sulfide coating started glowing. That indicated that there are some charged particles hitting this zinc sulfide layer. Is it clear? And that is behind the anode. Is it clear or not? Why they were these particles are known as cathode rays? Because they were coming out of the cathode. It appeared to come out from the cathode. Is it clear? So that's why, and how their presence was shown. Their presence was shown. Overall, there is some flow happening that is shown by the glowing of the tube, and their presence is shown by applying the zinc sulfide coating on one end. The zinc sulfide is a phosphorescent material, and it has a characteristic to glow when some charged particles hit it. Okay. So it was observed that the cathode rays uh, were coming out, okay, and they were moving towards the anode. Okay. Now, what are the other evidences of cathode rays? Let me tell you in the detail. Okay. These are the properties of the cathode rays, and they were discussed in by J. Thomson. So the properties are cathode ray travel in a straight line. they move from cathode to anode. They are negatively charged. Okay. Actually, they are coming out of the negative and going towards the positive. Okay. So basically, negative, they are coming out of the negative and going toward positive. Mean negative, they are of themselves negatively charged particle. That's why they are moving away from the negative electrode and going towards the positive electrode. They travel in a straight line and they cast sharp shadow.
So what does a sharp shadow mean?
Yeah, placed in their path. Okay. Suppose when we see that when a light source is coming in a straight line from one side only, when we look at the shadow, our shadow is very clear. Is it clear? Have you seen? But nowadays we have a lot of LEDs and light is coming from all the directions. So now we don't see very sharp shadow. Is it clear or not? So sharp shadow means you have a fixed boundary. So why the sharp shadow? Because cathode ray move in a straight line. So they cast sharp shadow. They are negatively charged particles. So what happens is these electrons are moving like this from negative electrode
So
to
do they
positive.
glow?
Yeah, actually they do not glow. But what happens is, suppose I put an object in their path, and behind that object, I put a zinc sulfide screen. Is it clear? So this is an object. So this object, this portion, this triangular portion will block the electrons, and the remaining portion will have that electrons hitting on the zinc sulfide. So they, because they are moving in the straight line, so exactly you see that there is the zinc sulfide screen start glowing. Okay, and there is a shadow of the object being generated on this zinc sulfide screen. It is because they move in the straight line. Suppose if one electron is going like this, another is going like this, or if they are moving, so then you will not have that perfect shaped shadow. Is it clear or not?
Yeah.
Yes, sir.
It is just like, suppose if you have a light coming from one direction, you place an object and you see that there is a sharp shadow on the other side. Okay, they are made up of material particles. How it was proved that they are negatively charged? Cathode rays are negatively charged particles. How it was proved?
As it gets attracted to anode,
Sir,
which is called.
explain.
Yeah, actually they are moving from cathode to anode. Okay, that is because they are coming out from the negative. Means they are going away from the negative and going towards the positive. Okay, mean they are get attracted toward the positive electrode. So that indicate that this positive electrode, they are negatively charged. Is it clear?
Yeah.
Okay.
Yes.
So now there is also one more way by which we can show that they are negatively charged particles. So this is the cathode ray. This is a negative, this is the positive, and electrons are going like this, right? And now what happens is, suppose up in spite of other than these negative and positively charged plates, I put two more electrodes perpendicular outside the tube, okay, like this. Suppose this is positive and this is negative. So without them, the cathode rays were moving in the straight line towards the positive. Now what will happen? If I applied one more positive and negative charge perpendicular to the path of the movement of the electrons, what will happen? This being negatively charged, they will get deflected towards positive plate. Are you getting my point or no?
Yes, sir.
So this again proves that they are negatively charged particles. Okay, so then their charged particle, they get attracted towards the, okay, and positively charged plate mean they are negatively charged, and they get attracted in the magnetic field also. That also indicate that they are negatively charged particles. Okay. Cathode ray they are made up of material particles. What do you mean by that? Mean these particles are not they are made up of matter. They have some mass. Okay, and they have
So what
charge.
particles?
The
The
particles of the cathode rays, which are electrons. Cathode ray particles or electrons are made up of, they are actually material that is a fast moving stream of flowing negatively charged particles. They have a mass. What is the mass of each particle? That was discovered later on. Okay, I will tell it in the next experiment. Okay. And they have charge. Okay. Electrons are negatively charged particles. Is it clear?
Yes.
They get deflected in electric field and magnetic field. In electric field, they get deflected towards the positive plate, which indicates that they are negatively charged particles that we have seen. They cause ionization of a gas. If some gas is filled in this, that will also get ionized because that gas is being constantly hit by electrons. So that neutral gas or the atoms which were neutral, after being hit by electron, they will acquire some charge. Okay. They cause ionization. Cathode ray can cause ionization. Okay, of a gas through which they are passing. When these cathode rays are hit or directed towards a metal, okay, heavy metal, they produce, okay, they produce another rays known as X-rays. X-rays. These are also high energetic rays, but they are not made up of material particles. So X-rays are produced. Where do we use X-ray?
hospitals to check the bones.
Yeah, you have to check the bones, right? So they have very high voltage applied. You have a cathode ray tube, and you have a metal, heavy metal. So X-rays are produced when heavy metals like tungsten and molybdenum. Okay. So this is tungsten, the symbol is W. So cathode rays are hitting this. And these cathode rays, this metal will generate X-rays.
So tungsten, molybdenum.
Yeah, these are the two elements. Okay, heavy elements. MO, this is MO. You can find it in this is W. So cathode ray when they strike the heavy metals, from the surface of heavy metals, you observe that some other type of rays are being generated. Okay, and those are X-rays. Is it clear?
Yeah.
One of the
Yes, sir.
so these are some physical properties. Okay? Very most important point I'm writing here now is nature of the cathode rays. Is independent of so what is the meaning of this? What it indicates? What is the conclusion which we can draw from this point? This is a very important point. Very important.
The gas doesn't affect the cathode rays.
Pardon?
Does it mean the gas doesn't affect the cathode rays?
Yeah, gas doesn't affect the electrode which is there. That electrode, these electrode, the material of this electrode which we have taken, that doesn't affect the nature of the cathode rays. So means the cathode rays are consist of some particles which are there in all the elements. Means these are fundamental particles. So Nabila, what conclusion can we draw? Have you understood? So
Yes.
whether you take the iron electrode, whether you take the gases, argon, hydrogen, helium, lot of gases are there. So the cathode rays are being generated if you take hydrogen, helium, neon, argon, any gas you can fill in this tube. But the cathode rays have that same characteristic, same particles, same type of nature. It means that the particles which are made up, which are constituents of the cathode ray, they are present in helium also, hydrogen also, neon also, argon also, xenon also. Is it clear or not? So what conclusion can
Yes.
we draw? The conclusion can, this is a very important point, most important point, and this is actually uh, uh, the final conclusion of the CRT experiment that cathode ray particles. This is the final conclusion. They are the fundamental particles, mean they are the constituents of all type of matter. Means if we take hydrogen, it also contains the cathode ray particles, and these cathode ray particles were given the name of electrons. So electrons are fundamental particles of the matter. They are present in all the. Suppose if cathode ray is being generated only by hydrogen but not by neon, not by argon, then we could not have generalized this experiment. We have generalized this experiment. It means that these electrons are present in all type of gases. Okay, they are the fundamental particles of the matter. Is it clear or not? Cathode rays or electrons are the fundamental particles. Now there is another challenge. This cathode ray experiment only led us to the conclusion that electrons are present in an atom and they are negatively charged particle, and because they are negatively charged particle, that's why they move away from the negative electrode and go towards the positive electrode, and it appears that they are coming out of the negative electrode, and that's why the name cathode ray was given, and they are going towards the anode. Okay, and they are negatively charged particles. Now we have next challenge in front of us, and that next challenge is that what is their negative, what is the charge on this negatively charged particles. Okay, what is what is this what is the negative, how much negative charge is there on this. Okay, so there was another two experiments later performed which helped us to know the charge and mass of these cathode ray particles. Okay. It was known that they are negatively charged particles. But how much negative? What is the magnitude of the negative charge particles? Is it clear? So one experiment was another experiment which was performed, that was by J.J. Thomson. Okay, it was known as E by M experiment. E by M experiment was performed by J.J. Thomson. Okay. E is, or it is also known as, if I, this is E by M with the short form. Okay, if I write them in detail, this experiment helped us to know the ratio of charge and mass of electrons. E by M experiment. Charge by mass ratio. But this look very weird. Why? So if you want to know the charge, we should find the charge. If you want to know the mass, we should know find out the mass. Why the charge upon mass value is found out by this experiment? Charge is represented by E, M is representing the mass of the electron. So why not charge directly charge? Why not directly mass was found out? Why the charge upon mass ratio was found out? That appears very intriguing to us. Is it clear? So actually the
Sir.
reason is so why it was not directly charged, why it was not directly masked, okay. But actually the reason is uh, the nature of the experiment is such that it is not going to give you the mass, it is not going to give you the charge, it is going to give you the value of the charge upon mass, okay. So let's have the value, at least something is, we are not getting the charge, we are not getting the mass directly, but we are getting the charge upon value of the charge upon mass. So let's have that value first and let's work on it. At least something is better than nothing. They are negatively charged, that we know, but what is the value of charge, that we don't know. What is their mass, that also we don't know. Experiment was performed, E by M experiment, and with that experiment, charge by mass ratio was found out. Okay, so what happened is they took modified cathode ray tube, modified CRT. This was done in cathode ray only, cathode ray tube only. So they took some modified tube. This is the negative electrode, 10,000 volt. That same setup was there. Everything was same. Okay, this anode was there. This is the positive electrode. The cathode rays will come out, the stream of electrons will move away from the negatively charged electrode. And what they did, they made a hole in the anode. They made the hole in the anode to let this rays, the electrons pass through it. So some of the electrons pass through it. It is just like a small hole. So cathode rays actually, it is just like to out of the bunch of rays, you select few of them to move through the anode. Okay, anode is a hole is made. Now what happened is, and you have a cathode ray. In earlier televisions and black and white TVs, or you can see this type of tube when you open their box. Okay, this is type of tube, and this was the screen. Okay, that screen actually, the picture tube was actually none other than the CRT. So this kind of experiment tube was used, and on this to detect the electrons are hitting, we apply the coating of zinc sulfide, which is a phosphorescent material. And these electrons are actually, they move in the straight line, that we know. They hit the point A. Is it clear? That is expected.
Yeah.
Now what happened is they also applied electric field other than this positive and negative electrode perpendicular to the path of the cathode rays. Cathode rays are moving like this. Okay. So what I will do, I will apply one more electric field. voltage is applied perpendicular to the path. This is the positive plate and this is the negative plate. And when you apply this voltage also, what happens to this cathode ray? These cathode ray will get attracted towards the positive electrode and they get tilted and they hit the point P. Is it clear? But this is only when you apply this voltage. Why the cathode rays are moving upward? Because you have a positive plate here. So it will apply, it will attract the electrons, and instead of going in the straight line, they move towards the positive plate. Magnetic field was also applied. Okay, by applying a magnet, which was placed perpendicular to the tube. So you apply a magnetic field also. So if you apply the magnetic field, the charged particle also get deflected in the magnetic field. Okay. With the magnetic field, with only magnetic field, they were hitting the point C. Okay. How they will deflect in the magnetic field, that you will study in your class 12th. Okay. So but the direction was opposite to the direction of the electric field. Now what happened is, okay, this J.J. Thomson actually balanced the electric force and the magnetic force. They balanced the electric force and the magnetic force together. So electric force was taking the rays up, the magnetic force was taking the rays down, and when you switch them on together and you adjust them in such a way that both the forces balance out, then again the cathode ray will move in a straight line. So they balance the forces, and when you balance the forces of electric field and magnetic field, and you get the value of E by M. Is it clear? And experimentally, so you don't get the value of E separately. You don't, when you separate because the formula is such that you get the value of E by M. Okay, for the magnetic force and electric force, and that was 1.7588, okay, into 10 to the power 11 coulomb per kg. This was the E by M ratio of cathode rays, cathode ray particles. Or electrons. So we are still not able to find the charge. What is the charge? It is just like somebody gives the value of x upon y is 2. Suppose somebody gives us like this. So what is x? What is y? You can't tell. If x is 4. But if you can tell me the value of x and y, if I give you the value of any one. Suppose if x is 4, then y equal to 2. Got it? So this E by M ratio is like this one. We have the E by M ratio. How E by M ratio is? You need to remember the value. Don't get into the details, because details you are going to do it in 12th class in physics, because there is a separate chapter. So in EBIM experiment for the cathode rays, charge upon mass value was found out by adjusting electric field and magnetic field. This much only you have to write. And EBIM for the cathode rays is 1.7588 into 10 to the power 11 coulomb per kg. Okay, this coulomb is the unit for the charge and kg is the unit for the mass. Is it clear? Okay, just remember this much only. No need to get into the details and the experimental setup also. Okay, just how it was found out, but balancing electric and magnetic forces. That's it. This much you should write. So, but still the problem is not solved because we have the ratio, we do not have the exact value of charge and mass. Is it clear? So now the next experiment was performed by Millikan, and that is known as Millikan oil drop experiment. So another person, another scientist, Millikan oil drop experiment. Okay. So what this experiment was used for? This experiment, the purpose of this experiment is to find the charge of electrons or cathode ray particles. Okay. So how this is something related to oil drops that we know. Okay. Very simple experiment. What Mulliken did is he made a chamber. Okay. In that chamber, he put a oil spray. Or atomizer, just like the deodorant spray which we see. Okay, he put, and that oil spray will sprinkle or spray the very minute oil droplets into this chamber. Got it? In order to, because this oil spray will put lot of droplets. In order to select few droplets, he put in select few of them, he put a hole in the middle. So some of the oil droplets will in the middle can pass through the hole, rest of the oil droplets will stop up only. So these are the oil droplets which pass through this hole and come into this chamber in the middle of this chamber. Is it clear? And in the middle of this chamber, what else he did? So this is the hole. What else he did? These two plates through which the oil droplets are passing, they are charged positive and negative. And there is a window on one side okay, through which high energy X-rays are put on this air chamber. Is it clear? X-rays will ionize the air. Got it? So it is just like when we take a scale and when we rub them on a synthetic cloth or on dry hair, what happens? Some electron from the scale get transferred to the dry cloth, okay, and the scale get charged. Okay, similarly, when X-rays, high energy rays, when they are put into this chamber, the air get ionized, and this oil droplets, while falling, this is the enlarged view of the droplet. So this oil droplet is falling through that air, which is ionized, and while falling, it will absorb certain electrons. Number of electrons Ne. Is it clear? Ne means one electron, it could be two electron or three electron. Okay. Got the point? Because we don't know how many electrons are there, it can absorb certain number of electrons while falling through the air. And how the electron came into that air? Actually, that air was ionized with the help of the X-rays. Got it?
So, like, what actually is the purpose of ionizing things?
Yeah, to have the electrons generated. Okay, so we can ionize. Normally, we see when we wear synthetic cloth, they stick on the skin initially. It happens in winter days when uh, our skin is dry and right. You might have seen that. Clear? Or when you take a scale and rub it on your hair or synthetic cloth, that scale get also ionized because some electrons get transferred between the two surfaces, and this is falling, and you note the charge of these plates between which this droplet is present. The positive charge plate is above, right, and a negative charge plate is below. So actually this positive charge plate is trying to pull this upward. So this positively charged plate is pulling this negatively charged oil droplet. Why the oil droplet is negatively charged? Because it has absorbed certain number of electrons or cathode ray particles. Okay, so is electrical force is being trying to pull this oil droplet in the upward direction. Got it? And the gravity is trying to pull it down. Gravitational force is mass into mg. Got it? Or gravitational force, you can write. So what he did, he adjusted the electric force because this is the telescope with which he was observing the whole thing phenomenon. This is the telescope or the microscope. I should say microscope. Telescope is used to view celestial objects at a very large distance. So microscope, it was observing the movement of the droplets. He was adjusting the electric force. Okay, and by balancing this force, if the net force is cancelled, these oil droplets will not get accelerated downwards. So try to stabilize the force on oil droplets. This electrical force will depend upon, it is proportional to the number of electrons, or electrical force is proportional to its negative charge. Which is proportional to the number of electrons which are taken by this oil droplet. Is it clear?
Yes, sir.
So Millikan tried to stop these oil droplets in the middle only. And by balancing this electrical force, he found the charge on these oil droplets. Charge on the oil droplets was found by this method. Charge on the oil droplets was always found to be in the multiple of what do you mean by this? Means example, I should say. The charge is minus 1.6 into 10 to the power minus 90 in some case. In other experiment, it was, let's say, 3.2 into 10 to the power minus 90. It was 8.0 into 10 to the power minus 90. It can be, let's say, 9.6 into 10 to the power minus 90. Are you getting my point? Maha, Nabila, are you getting my point?
Yeah, it's gonna be in the table.
Yes.
Yes. So why it was always in the multiple of 1.6 into 10 to the power minus 19? So he tried to think.
Because that's
So
the least charge.
yeah, that is the least charge, exactly. So actually the droplet may take 1 electron, 2 electron, 3 electron, 4 electron, okay, or 10 electrons, or 5 electrons, or 20 electrons. So always the charge was found to be, so whatever the least charge was there, okay, so that was actually the charge of 1 electron. So that's how we thought that this must, the least charge must be the value of the charge of each electron. Is it clear or not?
Yeah.
Yes, sir.
So can the charge of this uh, oil droplet in the Millikan oil drop experiment, can it be minus, let's say, 1.6 into 10 to the power minus 20? Can it be like this? Or can it be 1.6 into 10 to the power minus 18 coulomb? Which is correct? What could be the charge of oil droplet out of these two is correct can be the charge of.
Maybe the first one.
Okay, first one is actually it is yeah, Nabila, would you like to add anything?
No, sir.
1.6 into 10 to the power minus 19. Okay, let's write in terms of the charge of a single electron. Okay, 1.6 into 10 to the power minus 19 into 10 or upon 10, what it is.
So I don't understand. Can you repeat?
This value, underlined value, is the 10 times or 1/10 of this value on the right hand side. Should I write it upon 10
10
or
times,
should
right?
10 times? So if I multiply it by 10, it should be 10 to the power minus 19. Are you getting a point? This is 1/10 of this. Are you getting a point or not? Because this is
Yes,
minus
sir.
19, and if you divide it by 10, the 10 will go in the numerator. It will become 10 to the power minus 1, and 10 to the power minus 19. It will become 10 to the power minus 20. Got it? And this is so this charge is actually the charge which I mentioned above is let me shift it. The charge which I mentioned above is basically E by 10. Are you getting my point or not? Do you agree with it, Nabila?
Yes, sir.
Maha, are you getting my point?
Yeah.
This is 10E or E by 10. 10E is this one, the lower one. It is 10 times minus 1.6 into 10 to the power minus 19 coulombs, equal to minus 1.6 into 10 to the power minus 18. Because this is 10 to the power 1 and 10 to the power minus 19. If you multiply them together, that becomes 10 to the power minus 18 coulombs. Is it clear?
Yeah.
So this is the second charge is 10 times E or minus E. And the first charge is E by 10. Is it clear?
Yeah.
So which one do you think could be the charge of the oil droplet in the Millikan oil drop experiment? It could be 10E or E by 10. Yeah, Nabila, tell me. What could be?
10.
Yeah, 10E or E by 10 or both?
It could be both.
Why both? And what about you, Ma? What do you feel in this case? 10E or E by 10 or it could be both? The charge
Both.
of the
Because it can change,
okay.
can be multiplied or divided.
Yeah, you can multiply it by 10, you can divide by 10. Okay. But let's think of in terms of oil droplet. If the oil droplet is falling through the air, it is accumulating electron. How many? 1 electron, 2 electron, 3 electron, 4, 5, 6, 7, 8, 9, 10, 11, right? Like that. Can an oil drop accumulate 1/10 of an electron? What do you think? Can you have just 1/10 of an electron, just electron being cut into 1/10 part and that can get into the oil droplet? Can that happen?
No.
That cannot happen. Either you can have 1 electron, 2 electron. Are you getting my point or not?
Yeah, I was saying to take the whole electron.
Yeah, it will take the outer electron. There's nobody who is cutting the electron into 1/10 and giving it to oil droplet. Low, let's take it, right? Not like that. Okay, either you will have 1 or 2 or 3. Okay, that is being absorbed by the oil droplet. So the charge of the oil droplet will be always the whole number multiple of the charge of E. It is not the fractional multiple of charge E. Are you getting my point or not?
Yeah.
So this is incorrect. Nabila, have you understood?
Yes, sir.
This means it is the 1/10 of the charge of E. So it means 1/10 of the electron got into the oil droplet. What about the 9/10 of the electron? Who cut that electron? Is there someone to cut? No. You can have either one electron completely being absorbed by the oil droplet, 2 electron, 3 electron, 4 electron, or 10 electron, 20 electrons, like that. So this is correct. 10 electrons if being absorbed by the oil droplet, you will have this much charge. But this is not the correct one. Is it clear? You cannot have 1/10 electron. So when he observed all these values, he came to the conclusion that all these values are the multiple of E minus E. Okay, so this minus E is the charge of the electron. Got it? It is minus 1.6 into 10 to the power minus 19 coulombs. And this is known as 1 unit of negative charge. Okay, suppose if you are giving somebody an electron, a single electron, you are giving that person minus 1.6 into 10 to the power minus 19 coulombs of charge. So always you can get 2 electron, 3 electron, 4 electrons. So always you can transfer the charge in the whole number multiples. Whole number multiples, you understood now? 1,
Yeah.
2, 3 of E. But not like you cannot transfer the charge as half E. Can you do it? Can you cut the electron in half and give half to someone? That cannot happen. Okay. So always the charge is being transferred in the integral multiple of E, or the whole number multiple of E, and that E is the charge, and that's how we came to the conclusion of the charge, about the charge of an electron, and the charge of the electron is minus E, and the value of E is minus 1.6 into 10 to the power minus 19 coulombs. Is it clear?
Yes, sir.
Okay. So this is the story behind the Millikan oil drop experiment. Now you get back to the previous experiment, E by M experiment. Once you have the charge, okay, Millikan helped to find the charge. You can put this value E equal to magnitude of E, modulus. Modulus means magnitude. Because charge we already know that is negative charge. 1.6 into 10 to the power minus 19 coulombs. E by M, you know, how much was it? The value of E by M? 1.758820. Okay, 1.756 you can remember. Okay, into 10 to the power 11 coulomb per kg. You put the value of E here and you get the value of M. M equal to mass of electron equal to 1.6 into 10 to the power minus 19. That is the value of E which I have put from the molecular oil drop experiment, divided by 1.75 or 1.76 or 588 into 10 to the power 11. This is coulomb. This is coulomb per kg. And just like the numbers unit also can get cancelled. Okay. You will have the mass in the kg. The mass of the electron is 9.1 into 10 to the power minus 31 kgs. Is it clear or not? That's how the whole story unfolded. It is much larger much smaller than the mass of the proton. Is much greater than the mass of the electron. Mass of neutron, though they are not yet found out, but we know from the previous chapter, this is negligible. Proton and neutron were almost same. Is it clear? Mass
Yes,
of an
sir.
electron is 1/1.837 times approximately, or 1840, 1836 times. Sometimes they write it like this. Okay. Approximately this much times the mass of proton. So that's why while calculating the atomic masses, you take the mass of proton and neutron only. Is it clear or not?
Yes, sir.
So how much was the mass of proton? If we can quickly recall from the previous chapter, mass of the proton was 1 point, though it is not discovered in this experiment. Okay, that was approximately 1 U. Okay. Mass of the neutron was also 1 U. As of now, you can write that. Okay. But the mass of the electron is not 1 U, it is 1/1836 times of 1, much less than mass of the proton. Clear or not? Okay.
Yeah.
Now, so this is about the cathode rays. But once the cathode rays experiment was completed, you completed all the uh, study of the nature of the particles. They were electrons. They were present in all the gases. They are negatively charged particles. Means all atoms consist of electrons. Okay. They are negatively charged particles, and their mass is 9.1 into 10 to the power minus 31 kgs. This is the mass of the electron. And the charge of electron was found in Millikan oil drop experiment, that was minus 1.6 into 10 to the power minus 19 coulombs. Okay. And later people started thinking that the atom was neutral. And if some electrons are coming out which are negatively charged, what happened to the remaining part of that? Nobody thought about the remaining part of that. Okay. What happened to that? Where it had gone? Are you getting my point or not?
Yeah.
So later people started thinking about that remaining portion. Suppose if you remove the electron, that became the cathode rays. But what happened to the rest of the part of the atom? Initially, nobody focused on that part because everybody was busy with the cathode rays. So that remaining part of the atom were called as anode rays. Okay. So discovery of protons, anode ray experiment. Same diagram, everything same, but initially we were focusing on cathode rays coming out of the cathode, right?